Imagine standing in a vast green field at sunrise, where the air is cool and fresh and the morning mist still clings to the grass. A farmer Ramesh walks slowly among his herd of cattle. To him, each cow is more than just an animal. It is livelihood, tradition, and survival wrapped together. He knows that the red coated Sahiwal cows give milk rich in fat, the Gir is resilient to hot weather, and the Holstein produces milk in large volumes but require careful care. But here's the challenge. While an experienced farmer can recognize breeds instantly by the curve of their horns, the color of their hive, and even the way they move, but this knowledge takes years of experience to build. For a new farmer, a veterinary student, or a dairy cooperative worker, identifying cattle breeds correctly is not so easy. Mistakes in breed recognition can lead to wrong breeding practices or poor farm management or even financial losses. Now, think of the scale of the dairy industry in India. India is the world's largest producer of milk, contributing to over 22% of global production. Millions of small scale farmers depend on the cattle for their daily income, yet, efficient breeding, feeding, and healthcare practices are still held back because of limited breed awareness. Imagine how powerful it would be if farmers could take out their phone, snap a picture of the cow, and instantly know its breed, expected milk yield, and best management practices. That's where artificial intelligence and machine learning step in. Why breed classification matters. Cattle breeds differ not just in appearance but also in productivity, disease resistance, adaptability, and economic value. For example, Sahiwal and Gir are prized for their high quality milk and resilient to tropical diseases. Holstein and Jersey dominate commercial dairies because of high yield. Indigenous breeds like Banni and Amritmahal are hardy, adapted to local climates, and need less maintenance. Misdefining a breed could mean feeding it incorrectly, pairing it with wrong bull, or feeding or mismanaging healthcare needs. For farmers, such errors can be costly. For governments and NGOs trying to improve dairy productivity, accurate breed classification is essential for policy making and cattle improvement programs. The story of cattle breed classification and AI began when researchers and technologists noticed a pattern. Farmers already used smartphones for everything: payments, weather updates, crop price, and even online learning. So, why not use the same device to identify cattle breeds? At first, the idea sounded too ambitious. After all, cattle look similar, many breeds have overlapping colors, markings, and size. But with the rapid growth of computer vision, powered by deep learning models like convolutional neural nets, the idea became practical. Just as AI can recognize faces in a crowd or identify objects in traffic, it can learn to recognize the subtle differences between cattle breeds. Enter machine learning. Here's where our journey begins. By collecting a large dataset of cattle images. If you want to know more about efficient net, check out this video by Code with Arohi, Rethinking Model Scaling for Convolutional Neural Nets. Step 1, Importing Libraries. Import OS to interact with directories and file path, NumPy for numerical operations and array handling, TensorFlow for deep learning library for building and training models, classification report and confusion metrics for the sklearn for evaluating classification performance, matplotlib.pyplot for plotting the confusion matrix, inter tools for entering over matrix elements when plotting, warnings.filter warnings ignore suppresses the unnecessary warning messages for cleaner output. Step 2 is defining the constants. Image size. All images are resized to 224 into 224 pixels. Batch size. How many images are processed at a time during training. Data dir folder containing your dataset organized by class folders. Learning rate speed at which the model update waits. Epos number of times the model will go through the entire dataset. Seed ensures the reproducible splits for training and validation. Step 3 is load model. It loads the images from directories and automatically labels them based on folder names, splits dataset into 80% training, subset equal to training, and 20% validation, subset equal to validation, resizes all images to image size, groups images into batches for efficient training, extract class labels from folder names, counts the total number of classes, and prints detected classes for verification. Step 4 is optimized data loading. Perfetch overlaps the data preprocessing and model training for faster GPU utilization. Autotune to lets TensorFlow decide optimal perfetch buffer size. Step 5 is data augmentation. Introduces a variety to training data to prevent overfitting. Random flips images horizontally and vertically. Random rotation rotates image randomly up to 50%, and random zoom in and out randomly. Step 6 is building the model. Loads the pre-trained efficient net V2B0 as feature extractor. Include top equal to false to remove final classification layers. We will add our own. Weights equal to ImageNet uses pre-trained weights from ImageNet dataset. Trainable equal to false freezes base model so only the new layers are trained. It defines the input layer, applies data augmentation, preprocesses inputs for efficient net, passes through the frozen efficient net base model, global average polling 2D reduces the feature maps to a single vector per image, dropout 0.3 randomly drops 30% of neurons to prevent overfitting, and final dense layer outputs probabilities for each class with softmax. Combines input and output layers into a Keras model, compiles model with Adam optimizer, sparse categorical cross entropy loss for integer labels, accuracy metric, and prints the model architecture summary. Step 7 is training the model. Model checkpoint saves best model during training. Early stopping stops training if validation doesn't improve for 10 epochs and restore best weights. Model.fit trains the model on training dataset and validation on validation dataset and prints training finished model saved as best cattle breed .h5 combines and confirms the training completion. Step 8 is post-training evaluation. Loops over validation dataset, stores true label in yTrue and predicted labels in yPredict, converts to NumPy array for metric calculations. Step 9 is classification report, calculates precision recall F1 score per class, prints detailed metrics for each class. Step 10 is confusion matrix, which computes the matrix showing correct versus incorrect prediction for all classes and plots a visual confusion matrix with correct/incorrect prediction, uses color coding to for easier interpretation. And step 11 is overall accuracy. Computes overall accuracy on validation dataset, prints final metrics as a percentage. From different breeds, Sahiwal, Gir, Holstein, Jersey, Amritmala, and others, and feeding them into a deep learning model, we can train a system to spot differences invisible to the untrained eye. The AI might notice the hump size of a Sahiwal, the ear shape of Gir, the coat pattern of Holstein, and the body build of Amrit Mala cattle. Over time, the model becomes a digital farmer eye capable of instantly classifying breeds with impressive accuracy. A farmer's perspective. Let's go back to Ramesh. Imagine he goes to the weekly cattle fair in his village. Buyers are walking around, haggling over prices, but there's confusion. A cow being sold as a pure Gir is actually a crossbred. Ramesh, unsure, takes out his smartphones, opens an AI powered app, snaps a picture, and within seconds, the system tells him the breed is 85% Gir and 15% cross. This not only saves him from a bad deal but also empowers him with knowledge that previously only experienced cattle traders had. Multiplying this scenario across thousands of villages, and suddenly AI is leveling the playing field for millions of small farmers. The bigger picture. Cattle breed classification is not just about identifying cows, it touches on bigger themes. Economic empowerment. Farmers can sell their cattle at fair prices, avoiding exploitation. Food security. better breed management, more milk production, stronger dairy industry, conservation of indigenous breeds. AI can help preserve rare breeds by ensuring they are correctly identified and bred. Research and healthcare. Veterinarians can provide more accurate treatment when they know the exact breed and its genetic trait. Challenges along the way. Of course, the journey is not without hurdles. Building a large, diverse dataset is tough. Cattle must be photographed in different lighting angles and environments. Some breeds are extremely similar, making misclassification possible. Farmers need a simple interface, not a complicated ML dashboard. But these challenges only make this project more meaningful. Every obstacle overcome is a step closer to making AI accessible to the grassroots level. The vision is that cattle breed classification goes far beyond a single project. It represents the larger role of AI can play in agriculture and rural development. If we can use ML to identify cattle breeds today, tomorrow we can use it to detect cattle disease early, predict milk yield for physical features, optimize feeding schedules with AI-driven recommendations, assist government livestock programs with real-time data analytics. This is not just the technology for the sake of technology, it's technology designed with empathy, built for people who never write a line of code but whose lives can be transformed by it. At the heart, cattle breed classification is a beautiful intersection of tradition and technology. For centuries, breed recognition was passed down orally from farmer to farmer. Now, machine learning gives us a way to preserve scale and democratize this knowledge. When Ramesh looks at his herd tomorrow, he may still smile with pride knowledge his cows by heart, but alongside his experience, he will also carry a new companion in his pocket, an AI system that helps him make faster, smarter decisions. And that's the story of how a simple idea, recognizing cattle breeds with ML, has the potential to reshape the dairy industry, empowering millions of farmers and bridge the gap between ancestral wisdom and modern innovation. Step 1. Importing libraries. Import OS, OS for file and directory operation, listing class folders, NumPy, numerical computation and array handling, CV2 for image reading and preprocessing, TensorFlow for deep learning library to load and run the trained model, warnings to suppress the warnings, Tinker, Python GUI library for building the window, buttons, labels and dialogues, PIL or Pillow to handle the images and display them in Tinker. Warnings dot filter warnings ignore. Cleans up the output by hiding unnecessary warnings. Step 2 is constants. Model path and data dir. Model path to your pre-trained cattle breed model and data dir directory containing folders of images, each folder representing a cattle breed. Step 3 is loading the model and classes. Loads the trained model using TensorFlow, reads folder names from data to get class labels, cattle breeds, shorts class names for consistent order, prints the number of classes and their names for verification. Step 4 is image preprocessing and function. First, it reads image from the disk using CSV, OpenCV, and then it checks if the image exists, raises an error if not. Then it converts BGR to RGB. OpenCV default is BGR, but model expects RGB. Resizes image to 224 into 224 pixels, matches the model input. Applies efficient net V2 preprocessing, scales pixels as required by pre-trained model, adds batch dimensions so it can be fed into the model. Step 5 is prediction function. It calls preprocessed images to prepare the image, feeds image into the model to get prediction, finds the index of the class with highest probability and calculates confidence percentage for the prediction, returns predicted class and confidence, shows a pop-up error message if something goes wrong. Step 6 is GUI callback function, which opens a file selection dialog for the user to pick an image, loads the image using PIL, resizes it for display in GUI, not for the model, but converts it to image tk.photo image to display in Tinker level, calls predict image for model prediction, updates GUI level with predicted class and confidence. Step 7 is GUI setup. It creates the main GUI window with TK, sets window title and size, adds a label for the title of the app, adds a label weight image label to show the selected image, adds button to select an image, connect to the browse image function, adds a label widget result label to display prediction and confidence. Root.main loop starts the GUI event loop so the app runs. So in summary, when the user clicks select cattle image button, opens a file dialog box to open an image. Image is displayed in GUI. Image is preprocessed and passed to the efficient net VB B0 model. Model predicts cattle breed and confidence. Result is shown in GUI.